Section: Introduction. In this section, we introduce visual reasoning, which is our ability to understand and interpret the visual world. This skill is crucial for navigating our surroundings and interacting with objects. Recently, artificial intelligence, AI, has made strides in mimicking this ability, particularly through vision language models, VLMs. These models combine visual and textual information to create descriptions, aiming to reflect human understanding. However, research indicates that VLMs and the large language models, LLMs, they rely on have significant limitations in reasoning and visual perception. Bongard problems, BPs, are a type of visual puzzle that challenge AI systems to identify rules based on a limited set of images. Created by Mikhail Bongard in 1967, these puzzles test cognitive skills in pattern recognition and abstract reasoning, presenting a tough challenge even for advanced AI. Each BP consists of 12 diagrams split into two groups, where we must identify a specific theme that distinguishes one side from the other. The diagrams may appear simple, but the concepts linking the images can be quite abstract, such as comparing the number of filled versus outlined objects or the direction of spirals. Unlike typical classification tasks, BPs require us to find overarching concepts that describe a set of diagrams rather than just recognizing patterns in individual images. While traditional machine learning has made some progress with BPs, VLMs have not been thoroughly explored in this context. Given that VLMs struggle with basic visual patterns, we anticipate that BPs will pose a significant challenge for them, offering a valuable opportunity to investigate which patterns are easier or harder for these models to identify. In our work, we assess how well different VLMs perform on BPs, focusing on their ability to uncover the underlying rules of these puzzles. We set up two types of tasks, one where the model must discover an open-ended solution and another where it selects the correct rule from multiple choices. We then compare the results from selected BPs to human performance to gauge how VLMs stack up against human reasoning. Additionally, we delve deeper into the model's pattern recognition abilities on 4 specific problems, providing insights into the strengths and weaknesses of VLMs and suggesting areas for improvement. We also review related work, noting that previous studies have explored Bongard problems using various methods, including formal languages and reinforcement learning. Traditional benchmarks for visual machine learning often focus on simpler tasks, while those designed for VLMs involve more complex challenges like image captioning and visual question answering. However, many of these tasks still require only basic reasoning skills. Recent benchmarks aim to test advanced reasoning abilities, but comprehensive evaluations of VLMs' reasoning capabilities are still lacking. Bongard problems, introduced in 1970, consist of 12 black and white diagrams divided into two groups, each sharing a common property that distinguishes them from the other group. The task is to articulate the underlying rule that differentiates the two sides, which can range from simple geometric properties to more abstract concepts. This complexity makes BPs a unique challenge for VLMs. In our approach, we use different strategies to prompt VLMs to solve BPs. For open-ended tasks, we provide a text prompt along with an image of the diagrams, guiding the model to analyze the diagrams and infer the rules. In the multiple-choice setting, we present predefined rule pairs for the model to select from. We also create a perception task to explore the model's limitations in visual descriptions, asking them to predict which concept applies to each image in the BP. Through these methods, we aim to better understand the capabilities and challenges faced by VLMs in visual reasoning tasks. Section Summary. In this section, we explore the capabilities of vision language models, VLMs, in solving Bongard problems, BPs, which are visual puzzles that require identifying underlying rules from sets of diagrams. We assess VLM performance through open-ended and multiple-choice tasks, comparing their reasoning abilities to human performance and identifying strengths and limitations in their visual reasoning skills. Section: Experimental Evaluation. In this section, we aim to explore how well state-of-the-art visual language models, VLMs, can tackle Bongard problems, BPs. Initially, we quantitatively assessed the models on all 100 puzzles and then compared their performance to that of humans, while also examining 4 selected BPs in detail. We focused on 3 main questions. Q1. How effectively can VLMs solve BPs? Q2. How do VLMs compare to human performance? Q3. How accurately can VLMs identify the concepts needed to solve BPs? For our evaluations, we used the original 100 Bongard problems and high-resolution images from a specific dataset. We tested models including GPT-4o, Claude, Gemini, and 2 versions of LLAVA. We used GPT-4o as our judge for evaluating the responses. To address Q1, we tasked the VLMs with solving each BP 3 times, and the judge evaluated their answers. The results showed that GPT-4o performed the best, solving an average of 21 BPs, but this was still low compared to human performance. A detailed breakdown revealed that even simple BPs, like distinguishing between small and large shapes, were often not solved correctly. We also tested the models by providing them with all possible rule pairs for the BPs, which improved performance for some models, particularly Claude, which solved an average of 28 BPs. When we reduced the options to 10 rule pairs, the models did even better, solving up to 69 BPs. However, it remains unclear if this improvement was due to better understanding of concepts or simply easier elimination of incorrect options. For Q2, we compared the VLM's performance to that of humans based on a user study where 13 participants solved the first 50 BPs in 45 minutes. Humans outperformed VLMs significantly, achieving an average accuracy of 84.41%, while the best VLM, Claude, only reached 20.16%. We categorized the BPs into 5 groups based on their rules, finding that humans excelled in existence and spatial BPs, while VLMs struggled, particularly with spatial reasoning. GPT-4o had the highest accuracy in the concept category, but overall, VLMs still fell short of human capabilities. In Q3, we examined whether VLMs could accurately identify the core concepts of 4 example BPs when prompted. Despite the model's poor performance on the BP dataset, we found that they struggled with perception and reasoning. None of the models solved certain BPs correctly, even though the rules were not complex. We provided individual diagrams to the models and asked for relevant concepts. The results showed that while some images were classified correctly, the models often failed to recognize all images accurately, indicating issues with spatial reasoning. For BP number 36, the models performed better, correctly identifying the concept of triangles versus circles, suggesting that familiar shapes may enhance their performance. Overall, we concluded that the current perception capabilities of the evaluated VLMs are insufficient for solving BPs effectively. Lastly, we acknowledge that while BPs are useful for assessing abstract reasoning, they represent a narrow set of challenges that may not reflect the broader range of problems VLMs face in real-world applications. Future work should include more diverse tasks and evaluate the performance of the judge and different model architectures to address these limitations.